Hi, my name is Kylie Bain, and this is my Physics 2212 Lab 5 report for magnetic braking with Faraday. So the contents of this video will be the introduction, and then we'll go through the experiment with the observations and question I had, then the glow script model and the what-if questions, and end with the conclusion. So to introduce the lab, we're going to use Faraday's law to get the current in each ring of the loop, the Biot-Savart law to get the force on each current-carrying ring, Newton's second law to iteratively update velocity and position, and the purpose of the lab is to collect data of magnet falling through aluminum foil tube, model the magnet and the tube's interaction computationally, and compare the computational predictions to the observed data. The results were my experimental time for the magnet to fall through the tube was 0.96 seconds, and the simulation calculated 1.686 seconds. So the experiment, my observations is that it took longer to get through the tube than I initially expected. It turned horizontal as it fell through because of the magnetic torque, and it went back to vertical after falling out of the tube. And why does the experiment not work with a ferrous tube would be because the magnet would stick to the sides and not fall through. And then those are my time trials, and the average came out to be 0.96. Glow script model, we're going to set measurements for the tube, create functions for the magnetic field and the EMF, calculate the gravitational force, find the current in each ring and the magnetic force in each ring, sum them to find the net force, and then update the velocity and position of the bar. So here is how we did that. It starts with creating measurements for the tube and then functions for that magnetic field. So there are those functions. And then this is updating values and net force and velocity and position and all that. Then this is the model that it produced. The black cylinder represents the foil tube. The red rings represent the increasing current below. It was a video, but I just put the end result in that as that black picture. The blue rings represent the decreasing current above the magnet, and that ending picture shows right when the magnet is about to fall out of the tube. And then the graph is velocity versus time. It makes it clear that as it goes into the tube, the velocity slows down a lot, and then it makes it to a constant speed. And then once it drops out of the tube, it obviously speeds up again. So the what if questions: what if the resistivity of the conductor were reduced as close as possible to zero, and how would the dynamics of the magnet change? So the induced current would increase, the magnetic force would increase, and the magnet would fall slower. And if there were holes or slots in the tube, the ring's current would be different. The resistance would increase, but there would be less because there were less complete rings. And therefore the induced current would decrease, the magnetic force would decrease, and the magnet would fall faster. And then to conclude, we observed how magnets react when falling through a conductor, calculated the motion-induced EMF and current. We utilized the Biot-Savart law, Faraday's law, and Newton's second law, and simulated the scenario with the computer model in perfect conditions. The results again were 0.96 seconds in my experiment, and theoretically 1.686 seconds, and that is just due to human error.